Hello everyone, this is Doc Fang. Today we talk about chapter 5, Newton's laws of motion. Okay, so before this chapter, chapter 2, 3, and 4, we learn everything about motion. We know displacement, velocity, acceleration, and we use kinematic equations to solve all kinds of problems. Okay, so we know motion well. There is one thing missing. What causes those motion? Okay, so the law governs the motion. From today, we talk about dynamics of the motion. Okay, those are Newton's laws. Okay, so in this chapter, we will learn force and mass. Okay, so some new concept we need to learn before we understand Newton's laws. Okay, and then we learn Newton's first law, second law, third law, and then we will talk about the vector nature of the forces and force in two dimensions, and then we will learn various kinds of forces. We'll learn weight and normal force. Next chapter we will learn more forces. We'll learn friction. Okay. You see, we have Newton's laws, right? So who is Newton? Isaac Newton. He was born in 1642, and well, actually from 642 to 1727. So it's about 400 years ago. It's about a little bit less than 400 years ago. All right. So let's talk about force. Force is nothing but a push and a pull. Okay, push and a pull. So if you want to apply a force to something, right? So either you push on that object or pull on an object. Okay. You see from here, there's an example. This man drag. Okay. Sled, right? You see there's a rope, and the rope contact with the sled, right? And then apply force. So, and also this force comes with direction. So force is a vector. It has magnitude and direction. Both of them put together, that's a force. Okay, and in this case, this kind of force is called a contact force. Okay, so you apply force through contact. Without contact, you cannot apply force to the object. Another kind of force is called a field force. For field force, no contact needed. Okay, you can have a contact, but not necessarily you need a contact to have a field force. The example here is this. This is Earth. We know Earth apply a gravity on anything. Okay, so this is a tennis ball. Okay, so the tennis ball, right? So Earth apply gravity on tennis ball. Okay, through distance, right? So in between, the tennis ball does not sit on surface Earth. Maybe it's floating air, right? However, Earth apply gravity on this tennis ball. Assume you hold this tennis ball, okay, and then you apply force for sure. However, the Earth also provide force on the tennis ball, that is gravity. Earth and the tennis ball does not have a direct contact between each other. However, Earth apply force through distance. You see distance here, and then that kind of force is called field force. Okay, and so far we only know gravity is a field force. Okay, later we will learn electric force and the magnetic force. Those are also field force. All right, second concept is mass. So what is mass? Well, mass is the measure of how hard it is to change an object's velocity. Okay, so how do we understand this? Here is object, right? Object sit there with v equal to 0. You want object to move. You want to change the object's velocity. Then you have to apply something. Actually, we know we need to push this object. You see? Apply force, right? And you give a direction. You push this force. When you push this force, to force this object to change its velocity. Then the object will respond with resistance. Okay, well, the natural tendency of the object is to maintain its velocity. Okay, so when you push the object, you feel resistance. The measure of that resistance is mass. Okay, because you want to change your object's velocity, object doesn't want to change its velocity. So object responds with resistance, and that measure of the resistance is mass, or it's a measure of how hard it is to change an object's velocity. If the mass is small, then it's pretty easy to change object velocity. Okay, if mass is big, it's very hard to change object velocity. And also, object can also be thought of as a measure of the quantity of the matter in an object. The stuff, right? Stuff object holds. Okay, so that is the mass. All right, so this table tells you the mass of the object. Earth, huge object, right? The mass is very big, very massive. Space shuttle, and that is about the mass of a space shuttle. And let's see, elephant, 5,400 kg. The unit for mass is kg, kilogram. Okay, kg. And a human body, a human, right? It's a 70 kg. It's a adult human, right? Adult. It's about 70 kg. Baseball, very small. And for the fluid, right? Gallon milk, 3.9 kg. It's about a gallon milk. Okay, the mass of a gallon milk. And honeybee, teeny tiny, right? Okay, so that's about the typical mass of an object. All right, so let's talk about Newton's law. So two concepts, right? Force and mass, and force and mass linked in Newton's laws. Let's talk about Newton's laws first. Okay, so let's consider some scenario. If you stop pushing an object, does it stop moving? Okay, so here's a surface, right? Assume there's a box, okay, and you apply force, and you push this box, right? What will happen if you have a big enough force? Box will move with some velocity, right? So what happens here is if you remove your force, what will happen to the object? Objects keep moving with velocity v or stop, okay? Well, actually, it depends on the surface. If a surface is very, very smooth, which means it's called frictionless, okay? It's very smooth. Consider you push a box on surface of ice, okay? And then if you remove your force, well, you assume you push the box with the velocity v, right? And then you remove your force, box will continue moving with velocity v. Okay, well, if it's rough surface, assume you move a chair around at your house, right? And then it's a pretty rough surface. If you remove your force, then chair stops moving almost immediately. Okay, if the surface is less rough, then chair probably will move a little bit forward and then stop. Okay, so that is the meaning. That's what happened. Okay, so if the frictionless surface is a very, very smooth surface, the object will maintain its velocity even you move the force. Okay, so this is called law of inertia. Object always maintain whatever its status, whatever velocity it has. Okay, so if we put an object there with a velocity 0, if you don't apply anything to the object will maintain its velocity equal to 0. Object will stay there forever. Okay, if object is moving with some velocity, right? Then if you don't put anything on this object will maintain this velocity. Okay, object stop because of the friction. If you have a friction comes from the rough surface. Okay, so the natural tendency for the object is to maintain its velocity. Maintain the velocity vector, maintain the velocity, which means keep the velocity constant. Velocity constant means the magnitude is the same and the direction is the same. Okay, so that's the meaning of a constant velocity. So if you move with a 20 meter per second, you will maintain the 20 meter per second. And then direction same, if you move towards north, you keep moving towards north, which means you move on a straight line. You don't change the direction. Okay, so that's the meaning of constant velocity. And that is law of inertia. That is law of inertia. Okay, so the object will maintain its velocity. Okay, if there's no any other external force applied to the object. Okay. Okay, now what happened here is the natural tendency of objects maintain its velocity, right? Maintain means keep the velocity constant. And then if you want to change the velocity of object, you have to put a net force. Okay, so basically this is Newton's first law. Okay, which means if net force, well, remember this net force equal to 0, V is constant. Okay, so if net force on an object equal to 0, then object velocity is constant. Vice versa, if velocity of the object is constant, then you can tell the net force on the object is 0. Okay, net force in physics we can represent this way. This is the sigma sign, which means you add all the force together is 0. Okay, so this must be a net force. When we talk about the study the velocity, right, we always put object into a reference frame. Okay, if Newton's law holds in a certain reference frame, this kind of reference frame is called an inertial reference frame. Okay, and the Earth, well, this kind of reference frame, right? So we have to find a reference frame. Okay, and the Earth itself is basically its surface of Earth is a very good reference frame. Actually, Earth does not move with constant velocity, right? So Earth itself, okay, and however, it's close enough. Okay, so accelerating reference frame are not inertial. Okay, so if you have a reference frame which is accelerated, then that is not a reference frame. Newton's law does not hold on that reference frame. Okay, Newton's law only holds in inertial reference frame. Okay, all right. Oh, that's Newton's. We talk about Newton's first law, right? So this is the first law. If net force on an object equal to 0, then the velocity of the object is constant. Okay, constant velocity means same magnitude, same direction. Okay, and this first law also you can look at the reverse way. If the velocity of the object is constant, remember, 0 velocity is also a constant velocity, right? So if object sits there at rest, which means the velocity of the object is also constant, okay? And then the net force on the object must be 0, okay? So now let's talk about the second law. Second law, we link a force and the mass together, okay? So what happens here is this. If you have two objects, right? So usually we use this scale. This is a spring force scale, right, to measure the force of the force applied. So if you have one object, right? So if you hand to the end of the spring, you see the displacement, right? You see the stretch of the spring right here, and then that measures the force. So the force on that spring is F1. Actually, force on the object is F1. If you have two same objects together, right? Put there, and then the force equal to 2F1. So the displacement here or stretch on that spring here is twice of the stretch of the spring here. Okay, which means um, you can calibrate the force. Calibrate this. We can use the object here if you know the well, later we'll talk about the weight. You actually apply weight on the spring, and you can use the standard weight to calibrate the force on the spring. Okay, so we use the spring to measure the force. All right, so now let's do some experiment about Newton's second law. So if we put a force on an object, so if in school you will see this kind of device, right? We call that an air track. Okay, air track give you very small resistance. Okay, so if we apply a force on a mass, right? So here's a mass. Okay, well, you can observe that there's acceleration generated on that force on the object. Okay, so you see you have a force applied on an object with a mass m. So if the force is F1, the acceleration is A1. Okay, so how to figure out the acceleration? Well, we learned in chapter 2, right? So if you can figure out xt relationship of the object, right? Then you can, from xt, you can figure out vt relationship. Okay, from a VT relationship, you can figure out AT relationship. So you can figure out acceleration at any given time. Well, if you double the force, so this is F1, this is 2F1. If you double the force, it turns out acceleration doubles. Okay, so what does it mean? This means F proportional to actually, we actually write the reverse way. Acceleration proportional to the force you apply. Okay, so double the force, acceleration double. If you triple the force, make it 3 times the force, 3 times bigger the force, acceleration will be 3 times bigger. Okay, that's the relationship between force and acceleration. Well, now let's look at the relationship between force and the mass. So what happened here is F1 m, right? You get A1. Well, if you double the mass, you have two same objects over there, right? So same force, then the acceleration decrease, basically cut in half, right? So it turns out acceleration inverse proportional to the mass, or proportional to mass over 1. You double the mass, acceleration decrease by 2. If you triple the amount of mass over there, and then acceleration will decrease into 1/3. Okay, so if we put those experiments together, here is a relationship, and this is Newton's second law. So acceleration equal to force over mass. Acceleration proportional to the force, inverse proportional to the mass. Okay, or you can write this second law in a different way. Force equal to ma. Force equal to mass times acceleration. Okay, so from this relationship, right, we can figure out what is the unit for the force. Unit for the mass is kg, unit for the acceleration is meter per second squared. You group all those units together, that is unit for the force. And people, in order to honor great Newton, unit for the force is Newton. Okay, N is Newton. All right. One more thing here is this. This force is this force actually is this force from this experiment, right? And then Newton's second law, the force here is net force, must be net force. So we have to write it this way. Sigma F equal to ma. Write that in a vector way, right? So acceleration, okay, and this is net force. Net force equal to m times acceleration. Okay, so because acceleration is a vector, so net force must be a vector. Net force meaning, what's the meaning of net force? Net force means you add all the force together. If you have a lot of force on an object, you add all of them together to generate net force, and the net force generate acceleration. And the relationship between acceleration and net force followed by this equation. That is Newton's second law. Okay, and then we talk about, well, the unit for the force, right? Unit for the force in SI unit. Well, it's kg, meter per second square, right? Put all together, it's Newton. Well, before SI units, we also have a CGS. C means centimeter, gram, and the second units, right? And in that units, use a dyne, okay? And also you have British units, it's a pound, okay? So in physics now, we only focus on SI units, Newton, okay? All right, so this is a table about the typical force in Newton, okay? Space shuttle. The space shuttle, if one puts a space shuttle into the space, right, then the force, it's called uh, propulsion force, right? Push force is about this 31 million Newton, or we call it a meganewton, 10 to the power of 6, right? So this is a meganewton. Okay, and then locomotive, like a train, right? So that's about 250,000 Newton. Okay, thrust of a jet engine, 75,000 Newton. Weight about a human being, right? It's a 700 Newton. Okay, that's about a weight of a adult human. Okay, and the weight of ant, well, small, 0.001 Newton. So we know this is a Newton. So we talk about what's your weight, right? What is your weight? Pound, right? You need to turn pound to Newton. Okay, 1 Newton equal to 0.225 pound. Okay, so you can tell what is 700 Newton equal to how many pound. Okay, times 0.227, right? So that is 700 times 0.225, right? So that is how many pounds, right? So well, you can calculate what's a pound equal to how many pounds corresponding to 700 Newton. And based on your weight, whatever pounds, right? You can assume 150 pound. You can turn 150 pound into Newton. Okay, so 150 divided by 0.225. That's how many Newton in your weight. Okay, that's my weight actually, 150 pound. All right. So we have to when we learn we have to solve Newton's second law's problem, right? So when we solve Newton's second law's problem, we have to build something called a free body diagram. Okay. So how to solve Newton's second law's problem? You build a free body diagram. You have to take out object out of its environment, regardless of what kind of environment, right? You have to take this object out of this environment. Okay, and then you label all the forces, sketch all the force, which means you have to identify all the forces on this object. Okay, and then you put a force on this object. You already have this force, right? We call this F1, F2, F3. If it turns out you only have 3 forces on this object, maybe you have F4. Okay, I'll tell you what kind of forces later, right? And you have 4 forces, and you sketch all the forces on this object. Okay, and then you choose a convenient coordinate system, right? So you usually that is the coordinate system as x and y, and you add all those forces together. Okay, so net force equal to F1 plus F2 plus F3 plus F4. Okay, those are vectors. How to add them together? Well, you see, you have a coordinate system, right? And then the net force is x component equal to F1x plus F2x plus F3x, right? And the net, well, you have x4x, okay? Net force is y component equal to F1y plus F2y, so on and so forth, right? So you can figure out net force is x component and the y component. And then you combine them together. So the magnitude of net force equal to square root of right? And then the direction of the force equal to inverse tangent function of y components over x components. So you know the magnitude and the direction. So acceleration's magnitude equal to okay, so you know acceleration. And the direction of acceleration will be same as direction of the net force. Okay, so you figure out the net force, right? Well, you do free body diagram, and then you do the calculation, and then figure out the net force, the magnitude and direction, and you solve acceleration's direction and magnitude. Okay, so this is Newton's second law. How do you use the second law? And for some example, if you know acceleration, right, and you know mass, and then you can figure out the net force. And if you know you know magnetic force, right? Then if you know some of the forces, right? You know F1, F2, F3, you can figure out what is F4. Okay, so that's Newton's second law's problem. Well, let's see example of a free body diagram. So if there's a book in your hands, right? So what is the free body diagram? What is the free body diagram of the book? Okay, so what you do here is you isolate the book out of its environment. Okay, so you take the book out, right? So here's the book, and then you sketch all the forces on this book. So the book, you have a weight. Everything got a weight, right? So this is the weight. Weight of the book is down, and also you put a force to push the book up, right? So that is the applied force from you. Okay, so those are the forces. Anything else? So from this example, we can tell that weight is a field force. Anything on surface of Earth or near surface of Earth, you always have weight. Okay, so you put just label the weight over there, and weight is always down. And then you look at this is a field force. Other than field force, you look at the contact. You see there is a contact between your hand and the book. So there is a contact force. So this applied force is a contact force. And this is your free body diagram. Okay, that's about Newton's second law. We will have example later. Okay, now let's talk about Newton's third law. Newton's third law states that forces always come in pairs. Okay, and acting on different objects. So what does it mean? So from this example, right? So you apply force on the book. Okay, so you push up, you have a force, right? Push up on this book. Meanwhile, the book apply force on you. So that's why you feel the force from the book. Okay, so the forces come in pairs. Okay, so this is the book from you to the force. Meanwhile, book apply force on you. Okay, so that's the meaning. So this is Newton's third law pair. If object 1 exerts a force F on object 2, then object 2 exerts a force negative F on object 1. Okay, so if you punch hard on the wall, right? You punch the wall, okay? So you apply force on the wall, meanwhile the wall apply force back on you. Okay, if you punch really hard, you feel very pain, right? Which means the wall punch back on you. Okay, so that is Newton's third law pair. Okay, so this is the wall, right? You apply force F1 towards the wall. Meanwhile, wall apply force F2 back on you. F1 and F2 same magnitude and actually opposite direction. Okay, so opposite direction, right? And on different object because F1 is from you on the wall and F2 is from wall on you. So this is on you. And this F1 is on the wall. Okay, so if you punch 200 pound on the 200 Newton on the wall, right? The wall punch back actually 200 Newton on you. Okay, and those two forces the same magnitude, opposite direction, and we call this the Newton's third law pair, and this is also called action-reaction pairs. Okay, so this is Newton's third law. Okay, so Newton's first law, second law, this is Newton's third law, and we need all of Newton's law to solve a problem. Okay, so here's an example about third law pair, right? When you drive the car, okay, right? So this is the force. This force, right, is from the car on ground. Meanwhile, this is the force from the ground on car, and exactly this force actually push the car forward, move the car forward. And when you push this refrigerator, right? And this is the force you apply on the refrigerator. Meanwhile, this fridge apply force on you. Those two forces, you see, same magnitude, opposite direction, and on different objects. And here is what happened to the weight. Okay, so gravity, Earth apply force on this object, right? This is this force is pointing down to the Earth, right? So this is the force from Earth to the object, to the space shuttle. Meanwhile, space shuttle also put a force on Earth, and this force is up. Okay, so this kind of force, we call that a gravitational force. Okay, gravitational force, or for short, gravity. Okay, gravity is weight, right? So Earth pull down on you. Meanwhile, you pull Earth up. Okay, so that is a Newton's third law pair between you and the Earth. Okay, if, right, so this is another example. If you apply force to the object, right, it's a force from person on object. Meanwhile, object will push back on a force on you. Okay, so those two forces, same magnitude, opposite direction on different object. One more thing is also very important. Those two forces must be collinear. Collinear means on the same line. Okay, so you see those two forces on the same line, right? So these two forces on the same line. Those two forces on the same line, same thing here. Okay, so what if the two forces not on the same line? Okay, then it's not Newton's third law pair. Okay, well, although the forces are same, right? Then the acceleration will not be unless object have the same mass. Okay, so this is from Newton's second law, right? Newton's second law equal to F equal to ma. Okay, from Newton's third law, right? If you apply force, right, to something, okay, equal to This is the force from you to something. Okay, well, assume this is a the box. Okay, or let's use this example: Earth and you. This is you, right? This is Earth. You have a mass m. Earth has a mass me, right? You have a mass, right? So that's more applied. Okay, so there's a force between you and Earth, right? So the Earth apply force on you, which is F down, right? So F, right? Then F equal to ma. So the acceleration on you is F over m. Okay. Meanwhile, you apply force on Earth, right? So that is negative F, opposite direction, right? So the force on Earth is F, magnitude, right, equal to m e a. So this is e, right? So ae is F over me. Okay. So because mass of the Earth is so big, right? So the acceleration of the Earth is very small. Okay, it is negligible. However, your acceleration is huge, right? So assume uh, you well, not you, right? So assume this is tennis ball, right? Tennis ball has a free fall, right? So just a free fall, just like a moving like this, right? And this is the force. Force from Earth on tennis ball is ma, and the acceleration of the tennis ball is force divided by mass, right? Meanwhile, Earth also get acceleration. However, acceleration of the Earth is so small, which is negligible. So you only see that tennis ball, right? Moving of a tennis ball, acceleration of tennis ball. Well, acceleration make the velocity increase, right? Changing velocity, so you observe the changing velocity of the tennis ball. You don't observe the changing velocity of the Earth because that's so small, negligible. Okay, so that's about Newton's third law pair. Newton's, and this is about Newton's third law. So now let's look at the different kind of forces, right? The first force we talk about is contact force. Okay, contact force is here, right? So if you have, assume this is a very, very smooth surface. Okay, so it's a frictionless. Okay, and you apply, and this is two boxes, right? So you apply a force on the two boxes. So now like I can give you some example, right? Assume the force you apply here is 30 Newton. Okay, and then those two boxes is this one is 10 kg, this is 5 kg. Okay, so what is the contact force between those two boxes? Okay, and one more thing here is, do you can you tell if there's a contact force the same if you apply 30 Newton on this side? Okay, so what's the contact force between them, and are those contact forces the same if you apply the force on different side of this group of box? Okay, and actually it's different. So how we calculate what's the contact force, right? So we can solve this problem this way, right? So you have one object, another object, right? You take this object out of the environment, right? And let's look at only the horizontal direction, because in vertical direction you don't have any motion. In vertical direction you don't have any motion. Okay, the coordinates in vertical direction is the same, right? So this object only has acceleration in horizontal direction. Okay, so how many forces are there on this object? Well, if we consider this object as a group, okay, so weight. Well, let's talk about only the force on the horizontal direction, right? So let's see. Just forget about weight first. Uh, we will talk about it later, right? We'll talk about weight later, right? So let's only talk about the force on horizontal direction. Okay, so object, right? So this is 1, this is 2. How many forces are there on the group of objects in horizontal direction? Okay, so this is 30 Newton, right? And then what is acceleration on this? Well, that's only force, right? So you can tell acceleration on this whole group equal to 30 Newton, well, equal to F over M. Total F is 30, M is 15 plus 10 equal to 15. 10 plus 5 equal to 15, right? Equal to 2.0 meter per second squared. Okay. Well, you can tell both of the boxes move with the same acceleration. Okay. So now let's look at the one of the box because we want to figure out the contact force in between. Okay, what's the contact force? The force between the two boxes, right? So box 1 apply force on box 2, meanwhile box 2 apply force on box 1. Okay, so when you consider the whole two boxes as the whole unit, right? Then you only look at the external force. So this is the external force. Internal force actually they cancel each other. Okay, if you consider the two boxes as a unit. Okay, and then you look at if you want to figure out the contact force between them, right? So you can just take object 1 out, right? So here is your object 1. Okay, how many forces are there on this object 1? Well, if you look at this object 1, there's only one force, right? So that is the force from 2 on 1. Okay, so the label here is means contact force from 2 on 1. From 2 on 1. Okay, so you put a 1 first, right? And then tell the source of the force is 2. Okay, that's the only force you have, right, on object 1. Okay, and then what is the motion status of object 1? Object 1 is A equal to 2.0 meter per second squared. So from this we can tell F12 equal to M1A. Okay, so this equal to 10 times 2 equal to 20 Newton. Okay, so in this example, the force between them, right? The contact force between box 1 and box 2 is 20 Newton. Okay, which means the box 2 apply 20 Newton on box 1, and meanwhile we can tell F21 is also 20 Newton, but it's in opposite direction. Okay, and we can check if what happened to the box 2. Box 2, right, is here. How many forces on this box 2? Only this example, right? So we have two forces. This is 30 Newton, and this is F21 from 1 on 2. This force is the Newton's law pair of that force, right? So this is 20 Newton left. This will be 20 Newton right. Okay, so what's net force on box 2? Net force on box 2, right, equal to 30 and minus 20, right, equal to 10 Newton. Okay, assume this is a positive direction. Okay, so you have to do the subtraction because 20 Newton towards the right, 30 Newton towards left. Well, why do I make this a positive direction? I just want the acceleration is positive. I want to build my coordinate system along the motion direction because A is in this direction. Okay, and then what is A? A for object 1 equal to net force is 10 divided by mass is 5 equal to 2.0 meter per second squared. Okay, so from this example, we can tell that contact force between them is 20 Newton. Okay, same thing here. What is the contact force between those two boxes? If you apply force in this end, 30 Newton from this end. Okay, well, same thing, right? So for this group, first what is the acceleration for this group, right? So same thing here, you consider those two as a unit, 1 and 2, right? So if we look at the force in horizontal direction, 30 Newton, so acceleration equal to 30 Newton divided by 15, right? So this equal to 2.0 meter per second square, okay? And then, so you can separate them, right? So if you look at object 2, how many forces are there on object 2? Only one force. That force is from 1 on 2, from object 1 on object 2, right? And then you can figure out what is force, right? So this equal to, and you know object's acceleration is 2.0 meter per second square. Remember, this is a connected problem, right? If the whole group move with this acceleration, then each of the object must move with the same acceleration. The motion status of each individual object should be same if they move as a group. Okay, so F21 is mass of the 2 is 5 times acceleration 2.0 equal to 10 Newton. So you can tell in this case, right, F21 is 10 Newton. F12 is also 10 Newton. Okay, so we can check, right? So what is the F12? So you can draw the 1 here, right? So box 1. How many forces are there on this box 1? You have, this is 30 Newton to this direction, and you have a contact force from 2 on 1, 10 Newton. Okay, so you can tell acceleration on 1 is net force 30 minus 10, opposite direction, right, divided by 10 equal to 2.0 meter per second square. Okay, so for this group, for this scenario, contact force between them is 10 Newton. For this scenario, contact force between them is 20 Newton. So contact force will be different if you apply force on a different way. Okay. Also, force is a vector. So far we talk about one-dimensional, right? So what if the force is two-dimensional? Okay. So what happens here is this. Okay. You have two person, right? Two people, right? Assume you have two people. This guy apply force in this direction. This guy apply force in this direction, and you want to know the motion status of this object, right? Okay, and this happen in space. Space. Okay, so astronaut provide a force here, another apply force here. Okay, and you want to know the acceleration of this object m. Okay, so in this case, this is a two-dimensional problem. So what you do here is you need to find the net force equal to F1 plus F2, right? So this is your free body diagram. Okay. So far we only consider, you can consider object as a point, right? So you apply the force on something called center of mass, center of gravity. We'll talk about it later. But you have to apply force at a certain point of the object, right? So this is the force from first astronaut, and this is the force from second astronaut. Okay, so you have to add them together. How to add them together? Well, this is total force. Add them together by using graphic method. Most of the time you have to add them together by using components method, right? So what do you do about components method? You have to figure out those two forces components, right? So F1, right? Components of F1. So this is F1, right? So you have to, this is the x-axis, right? So this is the y-axis, right? So this is the F1x. It turns out F1 has no y components, right? And then you need to put F2 inside of a coordinate system, right? So this is the F2x and F2y. You decompose F2, right? And then the net force is x component equal to F1x plus F2x, and net force is y components equal to, well, F1y equal to 0, right? Equal to 0 plus F2y. So you know x component, you know net forces x component and y component, and then you combine them together. It turns out combine them together will be in this direction, right? So in this direction, this is F. You know the magnitude and the direction. So objects will be accelerated in this direction, and acceleration equal to net force over mass of object. Okay, so this is a two-dimensional problem. You have to follow the procedures, right? First, you decompose every force. Okay, well, first step is you draw the free body diagram, right? Label all the forces, and then you build a coordinate system. You decompose all the forces, and then you add all the forces x component together to form the net forces x component. And then you add all the y component together to form the net forces y component. And then you combine them together, combine the x component and y component together. So that is your net forces magnitude. And also you can figure out the direction by using inverse tangent function. Okay, I talked this a lot, right? Many times. So I hope by now you can really understand how to, at least you know how to do this. Okay, now we talk about another force, which is weight. Okay, so what is weight? Weight is basically the gravity. Okay, the force from Earth on you, right? And what exactly weight is? Okay, so assume here's tennis ball. Okay, and you hold this tennis ball, right? So what will happen? Nothing will happen, right? So if you remove your hands, okay, so if you hold tennis ball, right, how many forces are there on this tennis ball? Two forces. Weight is down, that's from the earth, right? And then you have a force push up on the tennis ball, so you can hold this tennis ball, okay? So you can tell if you look at the net force on the tennis ball equal to two forces, right? So assume this is the positive direction, right? So the force from you is up, or weight is down, right? And in this case equal to ma, and a is 0 because you hold it. This guy doesn't move at all. Okay, so acceleration is 0. So you can tell F equal to W, magnitude wise. Okay, so the magnitude, you provide a force to push up, right, on the tennis ball, and the weight to push down. Those two forces have same magnitude. Okay, so they equal to each other. So net force is 0, and then tennis ball can stay there. So now you remove your hand, remove this force. What will happen to the object? Then you look at the free body diagram. Now free body diagram is here. Object only has one force, that is weight. Okay, so the magnitude of the weight, well, this is weight, right? And then what happened to the object? You know object will move down with acceleration. And that acceleration, we already know that acceleration, right? So that acceleration is negative g. It's a free fall. Okay? And so this force, right? So the only force you have is W, right? And then equal to ma. Okay? So equal to, right? So the magnitude of this force is called weight. Okay, so what's the magnitude of the weight? Magnitude of weight equal to mg. Okay, so that's the magnitude of the weight. What's direction of the weight? Direction of the weight is down. Okay, so weight always point down. And what is the magnitude of the weight? Because you see, this is the weight, right? Magnitude of the weight, right? Equal to m. Magnitude of A is g. So that is weight. That is your weight. Okay, so if your mass is 70 kg, right? And what is the weight? Okay, so weight is 70 times 9.81 Newton. That is your weight. And you can turn weight to a pound, right? Divided by, actually it's a times 0. Newton, right? Then times 0.225, you turn Newton to pound. Okay, all right, so that's a weight. Well, sometimes we have a different weight. We call that a apparent weight. So what is apparent weight? Apparent weight is basically it's a normal force. So if you stand on a box, right? You stand on a surface, right? Then there is you see here, if you do a free body diagram on you, right? So how many forces on you? You have two forces, right? You have a weight, and then this ground apply force on you, right? So this is applied. This is a push up. This is a push up force, right? So this is called a normal force. Okay, we'll talk about the normal force later. And this force actually is your apparent weight. Okay, so this push up force is from the ground, right? And this actually is because you applied your weight, you apply force, right? Which is your weight to the ground, to the surface, right? Meanwhile, this surface will push up on you. That force is called apparent weight. Okay, so this apparent weight. It turns out apparent weight is the normal force. We'll talk about normal force later. Okay, so what happens here is this: your apparent weight may not equal to your weight. Okay, so what happens here is, for this example, you are inside of an elevator. Okay, right? And what is your apparent weight? Okay, so this is our elevator, right? So the elevator move up with acceleration 1.2 meter per second square, and assume your mass is 70 kg. Okay, so what is your weight? Your weight is 70 times 9.81, right? So this is mg, right? So this is your weight. And what is your apparent weight? Okay, well, we have to do the free body diagram. Okay, so this is you, right? How many forces are there on you? You have your weight, and you have, which is normal force, which is also apparent weight. Okay, and what is our motion status? A equal to 1.2 meter per second square, right? So remember, we build a coordinate system along the motion direction. So this is the coordinate system I build, right? So this is positive direction. Okay, why do I do this? I want net force in the same direction of acceleration. So it's really up to you to build a coordinate system you prefer. Okay, convenient. So in this case, net force, this is one-dimensional problem, right? Net force equal to WA minus W. Okay, and this equal to MA. A is up, right? So in this case, WA is MA plus W, right? So what is M? M is 70 times A, 1.2 meter per second square, plus 70 times 9.81, right? So let me use my calculator to figure out what is the apparent weight. So in this case, apparent weight is 70 times 1.2 plus 70 times 9.81 equal to 770.7. Okay, so we use the three stick figures, right? Equal to 771 Newton. And what is your weight? Your weight, right? Your weight is this one, right? So let's see, 70 times 9.81 equal to 6 point. So your weight is actually 687 Newton. Okay, approximately three stick figures. So in homework, you just keep the three stick figures. Okay, so that is your apparent weight. What if this acceleration, this elevator, right? Acceleration is down. Okay, so a equal to 1.2 meter per second. This way down. Okay, so in this case, you do your work, right? It turns out if you build the coordinate system, well, this way, right? So this is free body diagram, okay? And acceleration instead of up, it's down. Okay, and we build the coordinate system along the motion, right? So in this case, I build this the positive direction. I just want my coordinate system along the direction of the motion, okay? So net force in this case equal to weight minus applied force. So this is free body diagram, right? So this equal to MA, right? So apparent weight equal to W minus MA, right? Equal to 70 times 9.81 minus 70 times 1.2. And I do the calculation. So 70 times 7.81 minus 70 times 1.2, 602. Well, let's make a 603 Newton. You see, apparent weight is different when you are at a different scenario, right? So if you are not on the, well, if you are on an elevator move with a constant velocity, which means A equal to 0, then the apparent weight is your weight. Okay, and if you see, if you are in a different environment, the apparent weight is different. All right, now let's talk about what's normal force. Okay, normal force happened between the surface, right? So you apply the object, right, on the surface, right? So here is the surface, right? And you put an object on the surface. Okay, so object will apply force on the surface. Meanwhile, the surface will apply force to the object. This force is normal force. It's a push up on the object. Okay, so the normal force always perpendicular to the surface. So this is the surface, right? Or we call that interface, right? So object push down, there's a force, right? And then normal force push up. Well, in this example, normal force is not equal to the weight. Why is not equal to the weight? Well, you see, you have a force, apply the force here, right? Okay, so what is normal force in this case? Well, you have applied force, right? And you have to do the free body diagram. Free body diagram for this object is this, right? So I just consider this object as a dot, right? So how many forces are there on this object? This is the weight down, normal force up, right? And apply the force in this direction. Okay, you have 3 forces on this object, all right? And then in vertical direction, this object will have, well, you see, this is the table, right? Object move with in the horizontal direction. So in the vertical direction, you have net force equal to 0. Net force y equal to 0 because acceleration in vertical direction is 0. Okay, so net force on vertical direction to 0, right? So in this case, you have to figure out everybody's y component, right? So this is the x component, fx, and this is the y component, fy. So net force in y components, right, in y direction equal to n up plus fy up minus w down, and this equal to 0. Well, net force in y direction must be equal to 0 because ay is 0. Reason for that is you always move in x-axis for this object, right? Assume this is a table, okay? So normal force in this case equal to weight minus Fy. Okay, so in this case, normal force equal to this. This applied force changes the normal force. In this case, right, normal force is your weight, okay? Because net force equal to normal force minus weight, right, equal to 0. The object sit there, okay? So normal force is your weight. However, if you apply some other force, you change the normal force. Normal force, okay, always perpendicular to the interface, okay? So in this example, we can tell normal force is smaller than the weight, right? Okay, sometimes normal force is bigger than the weight. So normal force may be equal, greater than, or less than the weight. Okay, so if you apply force this way, okay, so if you apply force F1 to this whole group, okay, so what is normal force? Okay, so we consider this object as a dot, right? So you have a weight, normal force, and you have F1 here, right? Three forces on this object. And we know this object will move along the table, right? So object will move in x-axis, okay? No, then in y-axis, net force equal to 0, okay? So what is net force in y-axis, right? So you have decomposed everybody, so this is F1y, okay? And let's make the upper positive, down negative, right? So normal force is up, positive, minus F1y minus W, and then add all together is 0. So normal force equal to weight plus F1y. Okay, so this scenario, if we apply a force F2 in upper direction, right? So normal, and then you come back to this scenario, okay? So we can tell normal force will be smaller than the weight. So in this case, normal force is bigger than the weight. You just look at this scenario, right? So forget about this F2. Then you have this scenario, okay? So in this scenario, F1, the normal force will be bigger than the weight. Reason for that is this: you have applied force, you have components add on this normal force. Okay, so this force actually add this force plus weight equal to the normal force. Okay, so this force actually increase normal force. So when you put a force in this way, normal force will be smaller than the weight. Okay, because this force give you this components plus normal force equal to the weight. Okay, so this component reduce amount of normal force. Okay, so that is what happened on the flat surface, right? So how about the inclined plane? Okay, the ramp like this, right? So what is normal force? So this example, right? So you have inclined surface, right? So the angle here is theta, and you have object sit on this inclined surface. What is normal force? Normal force is always perpendicular to the interface. Okay, so this will be the normal force. Okay, so how many forces are there on this object? Well, assume we don't have friction. Okay, assume there's no friction, just the surface is very smooth, right? We'll talk about friction next chapter. So in this case, you have two forces, right? You have mg, which is weight, and the normal force, right? So if we do a free body diagram like this, right? Just consider this is a dot, right? So this is the weight, and this is your normal force. Okay, and what exactly normal force is? Okay, so in this example, we have to build a coordinate system, and the coordinate system I like to build is this. This is the inclined plane, right? I want to build a coordinate system along the inclined plane. X-axis parallel to this inclined plane, and y-axis perpendicular. Okay, so that's a coordinate system I build. And if I build this way, I know that objects only move in x-axis. Okay, because the object will move along this inclined plane. Okay, along this ramp. And in y-axis, which is perpendicular to the ramp, no motion at all, because y coordinates always same, which is 0. Okay, if you consider the orange is here, right? So this orange location. Okay, or it's not orange location, but the y-axis is perpendicular to the inclined plane, then the coordinates of y is the same. Okay, so we know is 0. Okay, then for this problem, right? And we just build a coordinate system, right? So this is the coordinate system I built. This is x, and this is y. Okay, and then if this is the theta, right? If this angle is theta, then this angle is theta. Okay, all right. So this is theta, and then we have to look at, well, for this problem, right? So we have to look at net force in x-axis and net force in y-axis. What is net force in x-axis? You just figure out everybody's x component, right? So we can tell the weight, you have two components. You have y components, you have x components. Okay, so what is the x component from the weight? So by the way, weight we always like to write as mg. Okay, so what is this x component? Well, this is the theta, right? So if this is theta, then this is theta, right? So then this is 90 minus theta. Okay, then this will be theta. Reason for that is this is 90 degree, right? So this is 90 degree, and this is also another 90 degree. Okay, so I hope you can see this clearly, right? So this is 90, and this is also 90, right? So this angle, this is the theta, this is 90 minus theta, and this is theta. Okay, so you have to decompose the weight into two directions. In x-axis is mg sine theta. In y components, right, magnitude-wise is mg cosine theta. Okay, it's done. Okay, so if y is upright, so that is negative mg cosine theta. Okay, so in x components, in x direction, net force is mg sine theta. Okay, and that's only force, only one force you have, right? So mg sine theta equal to ma x. So what is ax? Ax equal to g sine theta. Okay, and in y-axis, net force, right, equal to normal force up and minus mg cosine theta. Okay, components of weight down, and this equal to 0. So normal force equal to mg cosine theta in this problem. Okay, so in this way, normal force is smaller than the weight, right? Because the weight is mg. So this is on an inclined plane. Okay, so when theta equal to 0, which means a flat surface, right? So normal force equal to mg cosine 0 equal to mg. Remember, cosine 0 is 1, and if on a very large, when theta equal to 90 degree, right? Theta 90 degree. So basically, this is straight up. Then you can tell normal force is 0. So if you put an object here, well, there's no interaction between the object and the surface, right? So object will just move down. So in this case, normal force is cosine 0, cosine 90. Cosine 90 is 0. Okay, you will see a lot of example about this next chapter. Okay, so this chapter we just know how to decompose the force into x and y and figure out what is the normal force. Okay, so that's all. That's good enough. All right, so that's all for this chapter. Make a summary. In this chapter, we learned force and the mass. Right, first, force is just nothing but a push and pull. However, we have another. We have a field force. field force applied on each other through distance, through space. Okay, and then we learn the mass, right? Mass is the measure of difficulty or measure of the resistance in accelerating an object. Okay, and after that we learn Newton's first law, second law, right, and the third law. Uh, First law states net force equal to 0, then V is constant. Okay, if V is constant, then net force on the object must be equal to 0. Okay, second law states that what if net force is not equal to 0? Then net force give you acceleration. Net force proportional to acceleration. Okay, to solve Newton's law, Newton's law's problem, we have to draw free body diagram, and we will have a lot of practice in the next chapter about a free body diagram. Okay, and Newton's third law is talk about action-reaction pair. If object 1 apply force on object 2 with F force, and then meanwhile object 2 apply negative F on object 1. So those two forces, the same magnitude, opposite direction, collinear and on the same line, which means, and then on different object. Okay, then after that we learned contact force, right? What's a contact force? And then we learned force are vectors, 2 dimension, how we can add all the force together. Okay, and also we talk about Newton's law can be applied to each component of the force independently. So we mentioned that, right? So the net force equal to ma. From this, right, we can tell net force is x component equal to max. Net force is the y component equal to may. So you can apply those two Newton's laws in different axes. Okay, you can apply them independently because acceleration, right? They don't. You can. So this is a 2-dimensional problem. A 2-dimensional problem actually is nothing but 2 1-dimensional problem. Okay. So you can look at different axes, and then we talk about weight. Weight is nothing but gravitational force applied on the object, right? So we figure out weight equal to mg, and this is magnitude of the weight. Direction always point to the earth down, no matter where you are, right? So this is earth, right? When you're here, this is the weight. When you're here, this is the weight. When you're here, this is the weight. Okay, actually always point to the center of the earth. Okay, so this is the mass, this is magnitude of the weight, and also we talk about apparent weight. So what is apparent weight? For force field from contact with the floor or scale. Okay, so apparent weight basically it's the same as the normal force. Okay, so same as the force applied from the ground or from the floor up on the object. Okay, so this is applied. This is apparent weight. And the last we talk about normal force, right? Normal force always perpendicular to the surface. Okay, remember you apply this right. Always perpendicular surface. Okay, and the normal force can be bigger, less, or smaller than the weight. Okay, so that's all for this chapter. And send me email if you have question, and also just let you know I'm always available to have a Zoom session with you. Okay, to help you out.